right? So this is the set associative example. So first off, what is set associative? It's just a way of dividing data into multiple pieces so it can be easily organized and accessed while in the cache. It's a trade-off between direct map cache and a fully associative cache. It allows some flexibility and choice for location in the cache. This comes from the two-way, the four-way, etc. It keeps blocks of data in the set to be used again. It stores new items by least recently used, and it can be demonstrated through cache mapping, which is what we're going to do here. So the example we're going to go over, so a 1024 word cache has a block size of 128 words and is four-way set associative. The cache starts empty and uses least recently used replacement. So the following words are accessed in this order. These are all the hex values. They're all going to be word addresses that we'll be using. So the steps to be taken before cache mapping. So first you want to calculate the number of blocks. This is done by dividing the number of words in the cache divided by the block size. So in our case, we have 1024 divided by 128, which gives us 8 blocks. Next, you want to calculate the number of sets you're going to be using. So you take the number of blocks and you divide it by how many ways. And in our case, we have 8 blocks, which we just calculated, divided by the four-way, which gives us 2 sets. Next, we want to calculate the number of bits needed for each set. So then we do this by doing 2 to the x is equal to how many sets we have. So in our case, 2 to the first power is going to be equal to the 2 sets. So we're only going to have 1 bit to describe each set. And lastly, we want to calculate the word offset. And this is done by doing 2 to the x is equal to the block size. And we know our block size is 128. So we can find that x is going to be equal to 7. So we're going to have an offset of 7 bits. So this is the data we're going to be using for the cache mapping. All the way on the left is the hex addresses that were shown in the previous slide. Right next to it is the binary version of those addresses. Next block over is the block address. So that is the remaining address once the offset is removed. And the way you remove the offset is by starting at the rightmost bit and moving your way left. So like in the first one, you want to remove that 1, remove it, remove that, remove that, remove it, remove it, and remove it. So those numbers there are going to all be gone, and you're just going to be left with that 5-bit number. Right? So from that block address, you're going to identify both the tag and the set number. So the set number, again, you're going to take the rightmost bit. So in this case, it's going to be 1. And so the set number is 1. And the second number, you have 0. It's going to be 0, and so on. And whatever remains of that block address is going to be your tag. So, right, so here is the setup for the set associative problem. I just put that exact all the data onto here so we can easily see everything is set up as how it should be. We're just going to focus on moving things in the cache. So first off, we have, So first off, we have this 1AB. So we see that that's going to be in set 1 and that it has a tag of 001. So the way we're going to do this is we're going to copy, and a lot of this is going to be copying, pasting. I'm going to do tag is equal to 0001, and the age is going to be equal to 0 because it just got into the cache. Since set 1 didn't have anything put in it, it's just going to carry over to here. And then lastly, we're going to highlight this to show that something was replaced. So in this case, it's just an empty space in the cache that got replaced. So for the next number, we have 813. That has a tag of 1000 and a set of 0. So this set 1 is going to just be copied over because our operation is taking place in set 0. Then we're going to do the exact same thing. Move those empty sets up and add in our tag and age as 0, and as well as highlight it. Right. The next one, 213, that is also in 0. So what we're going to do is we're going to copy this over since 1 is not being changed. Then we're going to put that next one into the set. So we're going to carry over our information from the previous step. But instead of the age being 0, it's going to be 1. And the new information is going to be set to 0 because it was most recently put into the cache. And we're just going to highlight this here. The next example, 780. This one happens in set 1. So we're going to take this from the information from set 0. We're going to copy it right over because nothing changes. Then we're going to do the exact same thing as the previous step. We're going to move everything over except the age. This age is going to be updated to 1, and then the tag for this new address is going to be put into the cache with the age of 0. And we're going to highlight that. Right. So this next one here, starts happens in set 0. So we're going to take everything over from set 1, put it here. So as we can see, the tag is 1000 and it's in set 0. As we can see up here, we have a tag at 1000 in set 0. So this age is going to be updated to 0. The one above it is going to be updated to 1 because this was most recently called. And we're going to have a hit. Now before this, we only had misses because the items we were looking for in the cache weren't there yet. And we're going to keep having those misses until we find something in the cache that has the same tag and set number as something before it. So in this case, we have a hit, and we don't have to go and replace anything in the cache because it's already there. So for the next one, we have DC2. So this one has a tag of 1101 and a set as in set 1. So, oh, forgot to do this. So we're going to move everything over here because nothing is happening in set 0. So now we're going to take this and we're going to move it over here. We're going to have a tag that's equal to 1101 and an age that is 0. These ages are going to get updated, from 0 to 1 and from 1 to 2. And then we also have that part of the cache which is still empty. So the next block, once again, nothing is happening in set 0, just gets carried over. Here, another item is added in. So we're going to take this, copy it over, and then we're going to have tag is equal to 1010. and age is equal to 0. Ages of everything before is going to be updated. Right. And lastly, again, we're working in set 1. So this gets carried over and nothing gets done to it. And now we have something peculiar. So now our entire cache is full for set 1, and we still have one more thing to put in. So now to determine which tag is going to get replaced, you're going to look at the age. So this one here has the oldest age of 3. So that's what's going to get replaced in the cache. So these 3 are going to carry over. And this one and the tag for this part is going to be put into the cache. And then from here, all the ages need to be updated. And 1. And yeah, that's the end of our problem there. Oh, and I guess I did forget to include some of the things that were getting added. So of course, that got added. This one got added, and then this one got replaced, I should say. They all got replaced. So yeah, that is how you do the set associative example. And yeah, thanks for watching, I guess.